All right, so this is a continuation of working through problems that involve the product rule, quotient rule, chain rule, and your transcendental derivatives. Problems 1 through 12 were in the previous video, okay? So number 13 is we have v of t is equal to 4 pi over 3 times r of t to the power of 3. Hopefully this formula looks familiar, but if not, that's okay. We will get back to it later once we get to related rates. Basically, we are taking the derivative of v. Whoops, I don't like that color. The derivative of v with respect to t. 4 pi over 3 is a constant, so constants they're not going to change as we use these rules. They will just stay there and be involved with multiplying or dividing. So the first rule we will use is the power rule. So I'm going to bring the 3 down. And then we have times 4 pi over 3. And then we already used a rule, so that means nothing else will change. So I used the power rule. And then the inner function is going to be r of t. Therefore, we will multiply with the derivative of r with respect to t. All right, number 14 is y equals sine x times cosine x. This is another product rule, so f prime of g plus f g prime. Sine of x will be f, cosine of x will be g. So taking the derivative of y with respect to x, the derivative of sine is going to be positive cosine, and then we leave cosine the same, okay, because that's g. Plus f is sine of x, and then the derivative of cosine is going to be negative sine because it's a co-function. All right, so again, if this was a free response, which you will not see this as a free response, you could leave it the same. However, if it was multiple choice, it will look different. So let's go ahead and simplify. So we have cosine squared of x minus sine squared x. Now, if you think back to pre-calculus, there were some double angle identities that you were expected to remember, okay? And those are going to blend into calculus as well. In fact, we use them a lot more in calculus to help us integrate once we get down the road to that. So remembering them now is going to help you later. So cosine squared x minus sine squared x, that is a double angle identity for cosine. Double angle identity for cosine. Okay, number 15 is y is equal to e to the power of x times cosecant x. We have another product rule. So e to the x will be f, cosecant x will be g, and the product rule is f prime of g plus fg prime. All right, so dy dx, f prime, the derivative of e to the x is e to the x. And then we already differentiated one function, so cosecant x will stay the same. We'll have a plus. And then f is e to the x. Now the derivative of cosecant x, if you think back to secant, the derivative of secant x is secant x tan x. So it's itself and its partner. Cosecant's partner is cotangent. Okay, so it's going to be cosecant x cotangent x, but because it's a co-function, it's going to be negative. And even after teaching this course this is my 3rd year teaching, I still go back to finding that pattern. I don't really have any of these memorized. I just look for the patterns and recall them from that. Same with the quotient rule. Like, it's not, I think back to product rule and then I transfer that to the quotient rule. But if you're someone that memorizes quickly, some of you do, that's great. But if you don't, then that pattern recognition, that's going to be so helpful as you go through this course. All right, I don't know why I wrote that like there would be a quotient. There isn't. So if we clean this up a little bit, we have dy dx is equal to, let's see. Let's go ahead and do e to the x cosecant x minus e to the x cosecant x cotangent x. All right, so we can factor a couple things out. We can factor out an e to the x and a cosecant x. So we'll have e to the x cosecant x, And then what's left in that first term, if you divide it by e to the x cosecant x, I keep writing cosine, that's going to be 1, and then we're left with cotangent x. Okay. So again, for free response, you do not have to simplify like this. However, for some multiple choice, you could see them in their factored form. Number 16, we have g of x is equal to e to the tan x plus root 7x. All right, so we have a couple things going on with this one. First off, we have a composition, so that will be the chain rule. And we have another composition, which will also be the chain rule, okay? But they're going to happen separately. So let's see. Interesting. Okay, so let's do a rewrite. I don't have to rewrite it like this, but maybe some of you see it. So we have e, and then we have a function to the tan x. And then on the back side, you could technically rewrite this as square root of 7 times the square root of x. So if you want to avoid using the chain rule for that second part, you can. So that means we have e to the power of tan x plus root 7 times x to the power of 1/2. So I want to reiterate, you can either go straight into the chain rule or you can split them up. I do not care what method you do as long as it is mathematically correct. Okay, and if you see another way to do it, but it's mathematically correct, then do that way. All right, so g prime of x. So basically, another way to look at differentiating e is that you will end up with u prime times e to the u, okay? It's the same that we've been doing. If we have e to the u, we multiply by u prime, but you can also just simplify and write it as e prime times e to the u, okay? So in this case, u is going to be tangent. So the derivative of tangent, tangent's partner is going to be secant, so it's going to be secant squared x, and then we'll have e to the tan x. Okay, and if you want to do it the other way instead, I do not care. You can do e to the tan x and then multiply with the derivative, which is secant squared x, as long as it's mathematically correct. All right, on the back side, root 7 is a constant, so I'm going to have root 7 times the 1/2, and then this becomes x to the negative 1/2. So we have e to the tan x, secant squared x, plus this becomes root 7 in the numerator, and then 2 times the square root of x. Number 17, y is equal to the natural log of x cubed plus 3. Okay, so there's not much we have to do for this one, because remember the derivative, we'll say the derivative of x of natural log of u, such that u is a function of x, is equal to u prime over u. Okay, so in this case, u is x squared plus 3, so that means dy dx is equal to 2x divided by x squared plus 3. Number 18, we have y is equal to e to the power of x divided by x minus 2. This will be the quotient rule, which is f prime of g minus fg prime over g squared, such that e to the x is f, and then x minus 2 will be g. So dy dx, the derivative of e to the x will just be e to the x, and then we have g, which is x minus 2, minus f is going to be e to the x, and then g prime, the derivative of x minus 2 is just 1, and then g squared will be x minus 2 squared. All right, so if we distribute, we end up with x e to the x minus 2 e to the x minus e to the x over x minus 2 squared. And all of the terms have an e to the x in common, so we can factor that out. So we'll have e to the x and then x minus 2 minus 1 divided by x minus 2 squared. And if we combine like terms, we have e to the x times x minus 3 over x minus 2 squared. It's also helpful to practice this simplification because when we get to related rates, you will use some derivative tests and create some sign patterns. And to truly see those sign patterns, you'll have to be in factored form. So that's another reason why it's good that we practice this. All right, 19, we have h of x is equal to x squared times cosecant of 3x. We have another product rule, but there's also a chain rule embedded in there. Okay, so product rule, we have f prime of g plus fg prime. X squared is f. Cosecant 3x will be g. All right, so h prime of x. F prime is going to be the derivative of x squared, which is 2x, times cosecant of 3x, plus we'll have f, which is x squared, the derivative of cosecant 3x. So cosecant's partner is going to be cotangent. If we think back to secant, the derivative of secant is going to be itself and its partner, so secant x tan x, which means the derivative for cosecant will be cosecant x cotangent x, and because it's a cofunction, it will be negative. So we will have, actually, let me put this in the next row. So we'll have x squared, so we'll have negative cosecant x cotangent x. But what is x in this case? What's the, I guess x is a bad term to use, but the input. What's the input? 3x. So whatever the input is from the original function, that stays as the input when we differentiate and expand it, okay? Now the chain rule, we will now take the derivative of the inner function, which is 3x, so we'll do times 3. So if I clean this up a little bit, I have 2x cosecant 3x minus 3x squared cosecant 3x. We don't need those parentheses. Actually, we do, to show that it's inside of that trigonometric function. I'll do it up here as well. And then cotangent 3x to there. Now, if you don't include those parentheses, I'm not going to take off as long as your mathematical work is correct. Okay, I just do it for better understanding. Now, if we look at this, every term has an x, well, both terms, and a cosecant 3x. So I'm going to factor those out. So x cosecant 3x. The first term, we're just left with a 2, and then we're left with a 3x cotangent 3x in the second term. And that's the factored form. All right, number 20, we have y is equal to tan of e to the power of x plus 1. So we have another chain rule. So dy dx, take the derivative of the outside. The derivative of tangent is secant squared. So we already took a derivative, therefore the inner function will stay the same, taking the wrapper off the lollipop. And now you will differentiate the inner function. So the derivative of e to the power of x plus 1 will just be e to the power of x. And just cleaning it up, it's just e to the x times secant squared of x, times secant squared of e to the x plus 1. 21, we have y equals natural log of 4x plus 3 to the power of 5. Okay, so notation-wise, be careful. These two are not equivalent. They are not equivalent, okay? Nope. See, this notation's confusing. Okay, so when we get to assessments, I'll make sure that this is more clear. There should be a parentheses out here showing that the power of 5 is part of the inside of the log. So it's not like what I meant to write was these are not equivalent. Let me fix this. These are not equivalent. Okay, so this would mean the entire log is raised to the power of 5. This is the power of 5 is part of the input for the natural log, okay? So when we get to assessments, I will make sure that that is very clear. And if you're ever confused on where it's supposed to be, please ask, and I will make that very obvious for you all, okay? So this one, the reason why I point that out is because you can use a rewrite for this, okay? So with our log properties, we can rewrite this as 5 natural log of 4x plus 3. So I'm not differentiating, which is why I did not write the 4 here. I'm not differentiating. This is a log property rewrite that we can use in order to make the differentiation process a lot easier, okay? So instead of using the chain rule, we're still using chain rule, okay? But it's one less chain rule that we have to use, okay? So if we do dy dx, I have my 5, that's a separate entity. I will still use u prime over u, since I'm differentiating a natural log. U being 4x plus 3. So the derivative of 4x plus 3 will just be 4, and then u is 4x plus 3. And this can be rewritten as 20 over 4x plus 3. Please, please be careful. You cannot do this, all right? You can only cancel or factor when that factor is involved in every single term. Okay, I still see mistakes like that every single year. 22, we have h of x is equal to x to the 8th times natural log of x. We have another product rule. So we have f prime of g plus fg prime. X to the power of 8 is f. Natural log of x is g. Okay, so h prime of x. We use the power rule for f, so we'll have 8x to the power of 7. We already differentiated a function, so we will leave natural log of x the same, plus f, which is x to the power of 8, and then the derivative of natural log of x is 1 over x, or u prime over u. In this case, u is x, and then u prime would just be 1, so it's just 1 over x. Cleaning this up a little bit, again, just practicing algebraic manipulation, we have 8x to the 7th times natural log of x plus, this will be x to the power of 7. X to the 8th divided by x, your exponential properties, 8 minus 1, you get x to the power of 7. From here, both terms, you can factor out an x to the power of 7. So the first term is 8 natural log of x plus 1. 23. Okay, this is what I was talking about. So 23 and 21 are very, very different, all right? Because now this 10 is showing that we are taking the entire log to the power of 10, not the function that's in the log to the power of 10. So we will have to use the chain rule for this, and we do not have a logarithmic rewrite for this, okay? So again, this is not the same as this, okay? I can move the 10 to the front, okay? Because natural log of x to the power of 10, even though verbally it sounds the same as natural log to the power of 10, this would be 10 natural log x. So these two are equivalent, but they are not equivalent with this. Okay. Again, please ask. This is a pretty obvious notation though, as far as the parentheses. So, all right. So let's take the derivative. So dy dx is equal to. I will use the power rule. So we'll have 10 times the natural log of x raised to the power of 9. And then we'll take the derivative of the inner function, which is natural log of x, so 1 over x. Clean this up a little bit, we end up with 10 of natural log of x to the power of 9 divided by x. Now, notation-wise and parentheses-wise, if you left these parentheses off, if it was like this, I would have some questions, okay? Because then I'm questioning, is the power of 9 for the x, or is the power of 9 for the natural log? So make sure you're including parentheses to make sure that we can tell what's going on there. The last problem, this looks exactly the same as another one we did. Okay, it is the same. Okay, why are we doing this one again? Anyway, this is just a reminder, I guess, that you can use logarithmic properties in order to expand this, which would make the differentiation process a lot easier. All right, so from here, dy dx, we're differentiating natural log, so that's u prime over u. So we'll have 3 over 3x plus 1 minus 5 over 5x minus 1. All right, and that concludes the examples for the new rules. The next video will be on implicit differentiation. Everything that we just did was actually explicit differentiation. We're just differentiating with respect to one variable, but we will look at how to do that for multiple variables in the next video. Hope this was helpful.